Are you tired of getting stuck in data science and machine learning interviews because of the complexity, the nuance, and all the available resources on the internet? Don't worry, I've been there and I gathered a lot of machine learning interview questions that I answered myself and a lot of people answered during their interviews, and I tried to compact them in a series of videos. Today is the first part, which will cover 5 different interview questions. We're going to look at the code, look at explanations and everything. So if this sounds interesting to you, let me know in the comment section if you enjoy this type of format, if you want it to be longer, shorter, if you want me to cover more questions in one single video so that I can make those adjustments for you. If you're new to the channel, hi, my name is Anas. I am a consultant data scientist based in the UK. So in this channel, I share what worked for me, what didn't work, a lot of technical tips, hands-on tutorials, how to land a job in the UK, how to start freelancing, so a bunch of useful videos. So if this sounds good to you, remember to subscribe, it does help me immensely. And without further ado, let's jump into it. So number one, what are the assumptions of linear regression? When we say regression, we know that we talk about a specific type of machine learning, and in this case it's regression, where we try to predict a continuous numerical value, like the housing prices, for example. So this is one of the types of machine learning. We have also the classification, clustering, but in this case, it's good to know what type we're talking about so that your focus is straight into regression. And here when we say linear, is I want to have a linear relationship between our independent features and our target feature. And I'm going to show it right now in the screen so that this makes more sense. Okay, so I'm now on VS Code here. Let me zoom in a little bit for you. So I just picked a data set from the internet, from OpenML. It's the Boston housing prices in the 70s. So we're just importing a few libraries, Python libraries, to work with tabular data, with numerical values and arrays, and this is to visualize. And we're using scikit-learn here for machine learning. And we just bring the data and it looks like this. We're just showing the first 5 rows and we can see these are all the features. So here we have this one, median value, is our target feature. So this one is the one that we try to predict, and all the others will be our independent variables. So the independent variables are the ones we're going to use to try and predict our target feature. So this one will usually be the Y in our machine learning training, and all of these will be the X. So if we look forward, that's what we see. The Y is just the median value, and the X is everything apart from the median value. So I don't want to go too much into this. We'll try to answer the linearity. The linearity, as I said, assumes a linear relationship between the independent variables and the target variable. We also need to think of the residuals, and the residuals are the errors. The errors have to be also independent, and we can look into them by just plotting and comparing the predicted value compared to the actual values. So if we look in here, for example, we can see actuals vs predicted, and we can see what are the residuals. So a residual that is negative, as I've put in here, is overestimated, and if it's positive, we underestimate the housing prices in this example. So in a real linear problematic, we usually find that all these predictions are usually quite close to 0, and we can see in most cases here things are closer and we have a few outliers here. So we can say it's linear, but it's not perfect linear either. And I gave here a brief example here of tree-based models and deep learning models, and these are usually for non-linear problematic. And in this case, if you saw that the data was scattered a little bit too much, just don't use linear regression and move on to a tree-based or something else. Second, how do you handle multicollinearity in a data set? You can detect multicollinearity by using a correlation matrix or VIF. I will show you this right now on my computer. But what you need to know here is that if we have certain features that are very much correlated, then we don't need to keep both of them to try to predict the target, because both of them, since they are already very much correlated, they will end up just biasing the results. So it's best maybe to drop one or maybe average them together, or use a regularization method like L1 or L2, things that we're also going to discuss in this video. So here we're looking at the multicollinearity, and we just create a correlation matrix from the same data set of the Boston housing price. And we can see here that we have, for example, some high correlations here, 91% in this Riad and tax. So if we look at them, and we do the VIF as well. So the VIF is the variance inflation factor, and this quantifies how much a feature is correlated with the other. So we can either look at the VIF, or you can look at the correlation matrix. You can visually see the results with the correlation matrix, or the VIF, you can see directly what's the VIF score. And based on that VIF score, here I've put it here on the table for you, if it's 1 to 5, it's usually okay. If it's 5 to 10, there is collinearity. If it's above 10, there is high collinearity, and you want to avoid those. So here we can see that this tax here is 9, and this rad is 7.48, and these two have really high collinearity, and that's something that we can investigate. 3. Explain the bias-variance trade-off. This is a question that is asked very often for you to understand the nuance of underfitting and overfitting modeled in your data. This one is asked in so many interviews, and it's good that you understand this properly. It's a very simple concept, but it's good to build an intuition behind how it works. Bias refers to errors in a model being too simple, so we say that it's underfitted, while variance is error from models being too complex, and we say they are overfitted. The goal is to balance both so that the model generalizes on unseen data really well. So too much variance is not good, too much bias is not good. Finding the right balance is the aim. Number 4 is what is the difference between L1 and L2 regularization. So we mean by those the lasso and ridge models, and these are usually used to optimize our model's performance. So what is the real difference between them? So you can see in this visual that we talk about lasso when we say L1, and we talk about ridge when we talk about L2. They serve a similar purpose, but they do things a little bit differently. One is more robust than the other. So L1 adds a penalty based on absolute values of coefficients and can shrink some to 0, removing features completely. So it detects some not really useful features and it will completely drop them. Whilst ridge will add a penalty based on the square values and shrink all coefficients without removing them. So the nuance here is one will be more robust and rigid, and one will still keep all the features, but will just give them a lower coefficient so that they're negligible in the end, but will not remove them. So if we look here at the code, we can just simply call from scikit-learn, we can call ridge, or we can call lasso. We can give it an alpha, which is something that is tunable, that was something that we can play around to have better results, or something that we can look for to try to see which is the most optimal one. You can see this code on GitHub, you'll find the link in the description below. And this can improve your overall performance. You can see here, we can see the root square, the result, 68.4%. We can see here 68.2%, and we can see the mean square error of 22, or the root mean square error of 4.7 overall. So these are just also techniques to optimize the feature choice in your model, and it's good to know the difference between them. Number 5 is how does a gradient descent work and what are its variants? So gradient descent is an optimization algorithm that updates models' parameters to minimize the loss function. Variants include batch or stochastic gradient descent, or SGD, and also adaptive methods like ADAM or RMS prop. So here we can look at the gradient descent, and here we call the SGD regressor, so it is the stochastic gradient descent regressor because we are in a regression problem. We can see all the hyperparameters that we have in here, the learning rate, the ETA, the penalty, the maximum iterations, and so on. And we can also calculate the same metrics that we're looking for. So here we can look at the residuals as we did in the linear regression as well. So how did we use the gradient descent? We used it to minimize the loss function, as we mentioned earlier. By default, it's the square error. So instead of calculating the optimal weight using matrix algebra, like a linear regression that we did earlier, we start with random weights. We can compute the gradients, the slope of the loss with respect to the weights. We then take small steps in the opposite direction down the slope, and we repeat the process over multiple data samples. That's the stochastic part. So here we can look, for example, at that loss function, and we can see here after a few iterations, this epoch is the number of iterations and the number of times we run, that the results stagnate completely. So after this number that is here, which is roughly 10, we don't have much of an improvement, so there is no need to just keep running the model for no reason. So we can see here, you'll see an explanation of everything. We can see the error on the data model learns from it falls fast in the first 10 epochs, then flatten. That shows a gradient descent is quickly finding good weights and then settling. It could have been more, it could have been less, but it's for you a way to know what's the most effect. It's a way for you to fine-tune the hyperparameters.